That's a snowshoe hare, that's a lynx, and that guy loves to eat that guy. And the populations of these things oscillate over time, okay? And one lags behind the other. And I think those in ecology will have seen something along those lines. And that's what this is. I think these are collected pelts or something like that. You can just think of these as populations. And you can see the populations are oscillating, okay? So you could, I can't remember what the final explanation in ecology was, but one explanation you could give is essentially that when you've got, let's see here, if the population of lynx is high, they eat the hares, the population of hares goes down, and then the lynx are in trouble because there's nothing to eat, so the population of the lynx goes down, and then the hares go, oh good, we can live now, and so that population goes up and on and on and on, it oscillates, okay, with a lag. Okay, now the question is, can we do anything with this mathematically? Okay, this is a famous set of equations, so it's worth you seeing this. Okay, so if we have just prey, so just the bunnies, and there are no cats around, hares and lynx, they're in good shape, okay? So let's suppose that they thrive. Let's suppose that they can grow exponentially, and that's what this is, right? It's the natural growth law, okay? So let's suppose that if there's no predators around, the prey can just blow up exponentially. Okay, let's suppose that if there's no bunnies around, the cats are in trouble. There's nothing to eat, okay? And so their population decays. This is a natural decay law, and their population just decays exponentially to nothing. Now the question is what happens when you bring them together. Now we've talked about one population at a time. We've talked about exponential growth and decay. We've talked about logistic growth. But we've never talked about what happens if there's two populations. Okay, if these guys are both there, what goes on, okay? The cats eat the bunnies, okay? That's trouble, minus sign for the bunnies. And it's good, plus sign for these guys, okay? So the growth rate of the lynx benefits from the predation. The growth rate of the bunnies suffers from the predation, okay? Now that effect, you could say, is proportional to how often these guys run into each other, okay? And you could say that how often they run into each other should be proportional to each of their populations, okay? So it makes some sense to say, well, the more cats there are, the more often they interact, the more bunnies there are, the more often they interact in a sort of proportional-ish way. And this kind of thing, where you say the effect is proportional to each of them, and so it's proportional to the product of them, is called law of mass action. And you may have seen this in chemistry, where you talk about molecules reacting, right? The frequency at which the molecules come together might be proportional to the product of their concentrations. Okay. So I think in elementary reactions that are first order, the two reactants, you would have seen something like that. There you go. So this kind of thing is called mass action. Okay? And look at what we've got now. These things are tied together, okay? Because the differential equation for the cat has got cats and bunnies in it, and then the differential equation for the bunnies has got bunnies and cats in it. So these guys are tied together. And it turns out this does do something. This does show oscillations, okay? With a certain set of parameters, a certain set of values, you get a graph that looks like this, okay? So what do we got? Blue is bunnies, red is lynx, okay? And we get oscillations, and we get a lag. And so this kind of thing does actually predict what we want it to predict. So that's interesting. So a decent mathematical model, or actually a fairly simple mathematical model, gives you the kind of behavior you'd expect. Or not expect if you didn't know that these kinds of oscillations happened. This isn't necessarily a useful thing for predicting like numbers, okay? But it's good for noticing patterns. It's good for trying to come up with underlying reasons for things. These are called the Lotka-Volterra equations, the ones on the previous slide, and these came up initially when they were thinking about fishing in the Mediterranean. And again, you saw oscillations there. And one other observation that happened is as the less they fished, the higher proportion of predatory fish they caught, which is a weird thing, okay? And the mathematical model can predict that, okay? So this is a nice thing about models. You come up with something, it's rigorous, and you can test it, okay, with predictions like that. Okay. One problem with this model is it's a bit too simple, and if you try to make certain realistic changes to it, for instance, you try to make the growth of the bunnies logistic, you stop having these cycles, okay? So it's not structurally stable. So you have to do other changes. You have to model the predation differently. You have to model something like the Ali effect, if you've heard of that, not named after me. And if you do that, then you get something structurally stable. Then if you add little bits of realism, then you still get oscillations. Okay, so this is just an example of a model from theoretical ecology that has had some success, and there's lots of extensions to it. And that's that.